Okay, so our next speaker is Ehsan Salehi from LDRA, verifying worst case execution time, ensuring embedded software is safe and secure.
Thank you. Hello, everyone. My name is Ehsan Salehi from LDRA. I wanted to talk about the verifying the worst case execution time and the challenges that people are dealing with when they are going with the multi-core, when they are developing a safety applications. A little bit about LDRA. We've been in the industry for 50 years now. Our first product was actually creating a mechanic for finding a dead code through linear sequence and jump by Professor Mike Hanel back in 1975. And then we developed our product to go towards the safety and the standards certifications such as DO-178, NPR 7150, and such. Particularly today, we're going to talk about the multi-core and how to go with the verification and validations when you have to go with the certifications of the multi-core application. So we're going to talk about the challenges that are currently exist, how to mitigate the interferences with the multi-core hardwares, and then we're going to talk about some of the lessons learned that we had through the certification and summary. So multi-core development has been increasingly approached these days, and a lot of applications now we are dealing with are using multi-cores. The concerns that come across the development using multi-cores are the reliability, where basically we want to make sure the executions of the tasks are not dependent on any other cores, or if they are, we can be mitigating the risk. The predictability where the timing and the instruction sets and the rules comes up, we want to make sure we know which one would be the next instructions that are going to be executed. And also the failure of the reliability and predictability are going to be an issue. Definitely using a software safety application, you have to deal with creating a mechanic to detect the faults, and also having a multi-core could be a challenge there. So the real-time determinism, it's a problem. It's a biggest challenge that you have with the multi-core, and we're going to talk about why. I know we were talking about the behavioral determinism, but I think when you go to the standards, that vocabulary is not going to be something you can use when you go to the safety. So because of that, we want to make sure we can mitigate the interferences that are happening between the cores. And of course, you want to make sure you are designing that you have a tolerance for the faults, and making sure you are accommodating that for the safeties as a part of your risk assessments and detect the errors. So because of, in the single core application, timing analysis was easier. So you basically executing, and it really depends on the takes per second it takes for you to execute a task. So it was easy, not really was it challenging, and it wasn't really mentioning back in the time. So when it comes to the multi-cores, because of the fact that we have different resources that are going to be shared across the cores, we're going to have a timing of applications, but it may not be exactly always the same. So it becomes non-deterministic. We can exactly predict how long exactly for you to take to execute the specific tasks, or programs. And there are also other characteristics and things that can make our timing even worse, like the voltages, the temperatures, and even having the complex instructions can affect to our behaviors for the programming. So how can we certify the multi-core applications for safety and also airworthiness or the flight softwares. Well, the safety standards came up with first as an advisory document was CAS 32A. And the CAS 32A was giving you recommendations of calculating worst case execution time and basically not really so much of the requirements. AC 2193 was more of a directive approach where they have a set of objectives and requirements that you could use in order to be able to help in addressing, for example, NPR 7150 or even in the avionics software, DO 178, to satisfy or certify your multi-core applications. Essentially, even though a company started with aesthetic analysis wasn't really helping you anymore with the multi-cores because there are things that are happening that are beyond just the flow of the programs in a single core. So, and we are aesthetic analysis, so we had to be thinking what we can do in order to be able to help through this safety certifications. But before we go there, so we have hardware shared resources, memory, caches, and buses, and basically each one of them can contribute to the timing analysis that we have. Accessing and fetching the data from the memory through different cores. The caches that you are using, the L1 cache can be used per core, but if you are needed to be accessing data from different cores, you'll be using L2 caches. And also the buses that are going to be shared among the cores that you will be using. So these are going to be all together impacting the execution time. So finding the worst case execution time is exactly like why we are saying the timing is not deterministic. Basically, we want to find a degree of a certainty that you can take and say within this number of a time, my program is basically executed within this boundary. So the range of a distributed data of the execution times becomes important. Another thing is important is you cannot use the old fashions of single core aesthetic analysis to determine the tasks. You have to be able to do a better way of data flow and control coupling approaches that it can help you figure out the tasks that you can use to basically run or execute the tests for the execution times. So the AC 2193 proposed robust partitioning. Just to give you a little bit of an intro, we have space and time partitioning that we always had it as in the single cores, and the term of robust partitioning was coming from the ARINC 653, and so it would make sense in the single core where you have basically independent between the memories and the core to execute the robust partitioning, but realistically you can't basically do that in the multi-core. You can use the advanced operating systems such as DOS to help you with the cache optimizations and help you a lot with the reducing the usage of the L2 cache. But robust partitioning practically currently is not possible through the way of the definitions we have in the separation of the buses and memories. Even though the robust partitioning is not happening at the moment, but we have to go to the approach that we can come up with a boundary that we can say that our partitioning is robust enough that can be used for the software applications. So how can we measure the worst case execution time? What can we do when the classic aesthetic analysis can't help us? A couple of things. One was we always had are testing in a safety application based on the requirements. So we always had RBT or requirement-based testing in place. The requirements were coming from your system-level requirements to the software, and then the software was tracing it to the source codes. That can be still used for our approach to the measuring the worst case execution time. So here, as you see, the green procedures are the areas that we may have flowing through the different cores. And you can see the other components or the software configuration index are going to be going to the cores and connecting to each other. So a static analysis on each core together can give us a set of boundary that can be used for finding the worst case execution path. Same idea here, the control coupling analysis. The order of the procedures becomes important. You know, we had this back in the time in a single core applications, but now we actually can put it into a more practice in details. The fact that we know if we are calling it procedures, that the procedure are going to be interacting with the other cores, we can basically figure out the tasks from one core to another that can be taken place. So control coupling and control flow become important. And because of that, the AC 2193 is highly emphasizing in obtaining the data flow and control coupling analysis. We had to do this back in the time for the NPR 7150, but this control coupling and data coupling analysis, once you're making sure you are also putting the coverage that you are getting from your test cases are in place with your control coupling and data flow analysis. So you will be able to find the flow of your project and figure out from the components of your codes what components of your code are connected into the line, and then from the line to the another core. Then you're evaluating them based on the number of the calls they have. The cyclomatic complexity of those components can help you to figure out what sets of those tasks are going to be the highly good candidates for you to run the worst case execution time. Otherwise, you have to run your tests in the robustness matter on every single requirements you have. So you have to figure out a way of making your testing to be smarter, so you don't have to basically do just robust testing across through every single requirements you have. So these can help you to figure out the good candidate for you to be able to execute the worst case execution time. There are static analysis reports, for example, what we are doing as the LDRA, that can help you to find a good set of a candidate so you can run your robust test case for measuring the worst case execution times. For example, if you know a particular task has a higher number of the calls, has more cyclomatic complexity, that basically can be a good task that you need to run the worst case execution time analysis on it. Another thing that is important is having a good operating system that can give you a better timing measurement. Of course, you can use a timing that's going to be included in your test. So having, for example, DIOS, you'll be able to access a ticks per second from the kernel and then grabbing it to be able to measure the time. That becomes important and more in practice. So here, I have two simple examples, producer.c and consumer.c. Each one of them are going to be communicating to each other through different cores. So you can run the flow diagram analysis on them, and you can see there are on both sides of producer and consumer are going to be having some boundaries to be able to talk to each other. Looking at the data flow analysis, I'm not sure if it's visible enough. The variable message that is going to be used from the producer is getting covered here, and then on the other side, on the consumer is also received messages getting basically covered. It actually shows in green. So this helps you identifying the fact that when you're running this test, these two variables from these two different cores are basically getting covered at the same time. If that matches with your requirement, that basically help you to say, okay, yeah, this is the task that I can use for measuring the worst case execution time. Then becomes what would be the type of a test and measurement you need to take. There are different types, the stressors, the thermal stress, the interrupt testing. Even the power variation can all have an effect, but the most effect is the interference testing. And depends on the hardware that you're going to use and the operating system. Those type of testing needs to be identified. So you cannot come up with a general approach way of identifying the exact type of a testing. However, knowing the operating system, running the data flow control coupling analysis can help you figuring out what type of a test probably would be more applicable for your program. So you would be running a test in a nominal, but there's no interferences, and you would be introducing the interferences and taking the measurements. The more distributions you have basically means the more interference is actually occurring because the timing is going to be in all different places. So then you're finding the variance and the mean of your timing, and you define the 3 sigma boundaries that you can say in your report that most of my test cases, almost over 75 or 80% of our test cases are happening within this boundary. Therefore, if the boundary matches the requirements for the multi-core, then you are passing. Otherwise, you have to do some other things to modify your software and be able to get your requirement passing. So that's basically resulting of running a worst case execution time into a set of basically a test through the DIOS. And you can see the distributions, how it's falling here, how it's falling up. Sometimes the interference testing of just reading and writing to the data memory is not going to be enough. So you wanted to do other type of a testing like memory trashing or math trashing. These are the techniques that are introduced if you go, for example, to the grad school. They talk about it, where you basically writing a huge data to a memory or writing a gigantic calculations, like, for example, Fibonacci series. They can help you to figure this out. So in summary, we are going to go through the worst case, multi-core applications. Developing the safety is the key. So we have to figure out a way of making sure if you are using a flight software, you can basically certify your application. And the way you can do this is to identifying the limitations, what you have with your as interference can be problematic to your course, and then mitigating those risks. And the way you can mitigate it is using the data flow and control coupling analysis to be able to identifying the tasks, measuring the worst case execution time on those candidates. And I think that's it. That's all I had with that. Thank you.
All right, I'll do a question online first. They ask, I believe you made the statement that robust partitioning per the ARINC 653 definition was not possible with multi-core. If so, they believe the ARINC 653 standard has been updated to address multi-core systems. Is there anything written in the standard that can help here?
Yes, so it is true, yes. But the definition of the robust partitioning, if you're looking at the AC 2193, is coming from the single core applications. You can still mitigating those robust partitioning. We just have to say, instead of being a deterministic in a time, to come up with a certainty in a time. That's basically what is being used in the multi-core application for finding the execution times. You can't definitely say my program is executed at this amount of time, as you guys have behavioral time determinism. That's not enough for safety applications. You have to figure out the boundaries and be able to say that within the certainty, my project execution is going to happen, fall into in these boundaries. Okay.
Okay, we have one more online we'll take quickly. Besides path analysis on the C code, do you need to have models of the underlying hardware to accurately predict worst case execution times?
Yes, you do need to get the knowledge of the hardware and be able to, communicate with your operating systems and making sure what they are saying as a best approach can be taken to your software testing. So yes, relying on the back in the time robustness testing is not just enough for worst case execution time.
Okay, final question.
Thank you for the presentation. Pablo here. Is there anything in the standard about atomic operations like CAS and things like this?
I'm not sure. I have to look into it. I can get back to you later. But right now, the approach for measuring the worst case execution time, it would be categorized up to Class C on NPR 7150.
Thank you.
Thank you.
All right, thank our speaker.
Thank you.